Then the first speaker is me. I'm Taiji from the University of Tokyo and the deep learning theory team of AIVP RIKEN. Yeah. So in this talk, I want to talk about some reasoning capability of a transformer and some approximation theory by linear models. Okay. So you know that the transformers are very important architecture. So it is used in like a LLM and a vision tasks. And also the transformer is like a main architecture of a vision language models. So in that sense, a transformer is a kind of the key component of a modern AIs. Okay. Without the transformers, we don't have like a recent AIs. And actually, you know that the transformer is developed following the scaling law. Okay. The spending more computation for the training, then you get better transformers. So then accordingly, so you get more better AIs. So and by doing so, the number of parameters for transformer is also getting larger and larger. But on the other hand, you get better performances, right? So this is known as a scaling law. Okay, yeah, we are just following the scaling law. And nowadays, not only the pre-training, but also the post-training and the test time and computations are also important for in terms of the scaling law. Okay, of course, the pre-training is still very important, but in addition to that, so by doing like a post-training and like a test time computations, you get much higher performances. Okay, so then we also have a new scaling law for those computation resources. So here is one paper, it's a very famous paper from Google DeepMind about test time computations. So they considered about like a test time computation. So then they show that so if you spend more computation for test time, then you get better results. So let us consider like a reasoning task. So then the like possible answers, possible responses for a reasoning task are many. So there are many possibilities. So you need to search a very large hypothesis spaces to find the correct answers. Okay. So each path corresponds to one reasoning path. Then you should find just one correct path. So it is very difficult problem. So to find that, you need to spend more computations. So actually, so they show that if you spend more computations, then you will be highly likely to get a better result. Okay. So this is very analogous to human beings. So when you solve a mathematical problem, maybe you cannot easily solve the mathematical problem. So you will spend a lot of time. So then at some point, you will come up with some correct answers. The same thing also happens for LLM. This is called test time scaling. Okay. So there are some theories that support this kind of test time scaling law. So basically, that is performed by best of the test time scaling is achieved by like a kind of best of n strategies. Okay, so you know what is the best of n. Okay, so you produce n responses for some query x. So x is like a so like X is questions. For some questions, you produce n responses from like a base measure, so base model pi ref. Okay. Then you pick up the best one that maximizes your reward model. So where R hat is your reward model. Okay. Then you choose the best best answer that maximizes your reward.
Is it the immediate reward or return?
This is so this is a return. So what I'm considering just the outcome, outcome reward. Yeah. So this is not like an intermediate process reward model. Yeah. But anyway, so we maximize some reward. Yeah.
This is already a kind of global solution.
Yes. So so you have a kind of upper bound like this. Okay. So this is so upper bound over regret. Okay, so here pi bone is the best of n, distribution with the best of n policies, and pi star is the optimal policies. You see the difference over expected rewards between the best of n method and the optimal policies. So then that is bounded by like this. You don't need to remember this. So yeah, so we have this kind of there is this kind of bound. The important point is that in the right-hand side, there is a two quantity, the C pi star and the epsilon square. Okay, the C pi star is so-called coverage. So coverage is there's an expectation of the density ratio of the optimum policy and your base policies. So yeah, so the coverage measures how your current policy overlaps with the target, the optimum policies. Yeah, so it should be noted that the coverage is almost the same as the chi-square divergence up to constant. So by adding or like multiplying some constant, you get the chi-square divergence of our coverage. So you see that the coverage is like something like a discrepancy between your current policy and the optimal policies. Okay. So another quantity is epsilon squared. This is a error or reward model. Okay. So your reward is trained by some data. So maybe your reward is not perfect. So there must be some mismatch from the true reward. So that is measured by the epsilon square. So this is like it's like a square of the L2 norm between R hat and R. Okay. So then the regret can be bounded by C pi star bar over n plus square root of n epsilon square. So the first term will be small if you take n very large. If you produce more and more candidates, then you get a better result. So you see a kind of like a scaling law. So if you spend more computation for searching a good result, so then you get a better result. But it's not like it's not like there's no free lunch. So if you increase n, so maybe it converts to like it appears a kind of a reward hacking. That means that you will overfit to your reward model R hat. So then you should pay this penalty. Okay. So if your reward model is not perfect, so then you get this additional cost. So then, so in that sense, you should balance the first term and the second term to get the good result. Okay. Yeah. The similar thing also happens for the reinforcement learning with chi-square divergence regularization. So it is known that the best of n method is very similar to like a KL divergence regularized reinforcement learning. So okay, so what is that? So okay, so we basically want to maximize the expected reward, but you cannot trust your reward model completely. So you add some regularizations, like F divergence regularizations. Okay, so then you maximize this penalized reward, okay, with respect to your policy pi. So then in that case, by choosing this beta, the regularization parameter very correctly, then you get this upper bound. Okay, you also see that in right on the side, the regret is bounded by square root of C pi star under epsilon square. So you see there is also like a coverage and the error over your model. Okay, so then as in the previous slide, by balancing the regularization parameter very correctly, then choosing like this, then you get this upper bound. Okay.
The choice of F divergence is quite important.
Yeah, it's also important.
Usually you scale divergence.
Yes. So yeah, so we can also have some bound for K divergence, and it looks similar to like this by replacing n by like 1 over beta. So then you have the similar bound, but this paper says that chi-square divergence gives a bit tighter bound. So yeah. So, but I don't know. This is the tightest one. Maybe there could be better one. So, but currently, yeah, it is. So they show that chi-square is good. Yeah. Okay. So, but anyway, so what I want to say is that to make the right-hand side to be small, then the error epsilon square should be small. I mean you should have a good reward model. So otherwise, there appears a reward hacking. So to get a good reward, so you should train the reward model by n data points. Yeah. So then maybe the typical epsilon square could be like log over the number of hypotheses divided by n. Okay. So then by substituting this to here, then to make the right-hand side this to be delta, your required sample size is like a C pi star divided by the delta square. So times the log of number of hypotheses. So yeah, so you see that the sample complexity for the post training, so sample complexity for you to improve your reward model is like proportional to C pi star, so coverage. And you see that the coverage controls the difficulty of the problem very well. So in both situations, like reinforcement learning and the best domain strategies. Okay, so however, so then the next question is how large this coverage could be. Like the expectation of density ratio could be large in some situations. Actually, in like reasoning tasks, so let us consider reasoning tasks. So then this coverage could be large. So usually reasoning tasks can be modeled by like trees. Okay? So in each step is like a logical step. At each logical step, you choose the next step. So next step or logical step. So suppose that a very simple situation where in each step there is B choices. So then if the depth of this reasoning task is L, then the number of the final choice is like a B to the L. So you have the number of leaps is like a B to the L. So there are B to the L paths. So, okay. So now, if your base model doesn't have any knowledge about this reasoning task, so suppose that it has like a uniform distribution over the path, then it has like so then okay, so you put a uniform distribution on the leaf, so then each leaf has a probability mass like a B to the minus L, okay. But however, if there is only one correct path, like only this path is correct, so then the optimal policy is like a Dirac measures. So in that case, the density ratio at this point is like a B to the L. So by taking the average, so you have like the coverage is like a B to the L. So it is it's very large. So if your reasoning task is very deep, like L is very deep, so then the coverage can become large in exponential orders. So yeah, this shows the difficulty of this kind of reasoning task. Okay. To mitigate this kind of exponential dependency, what people is doing is like a curriculum learnings. Okay, you train your model from easy tasks to difficult tasks. Okay, you don't start from very difficult tasks. So you start from very easy tasks. So then gradually you increase the difficulty of the tasks. So then maybe the model can solve the problem gradually. Okay. Okay. So in our situations in this trees, you start from depth. So first depth problem, and then you increase the depth. Okay. So suppose that so only this path is correct. Then, as I said, the coverage is like a B to the L. So the density ratio between 1 and the uniform distribution is like a B to the L. So it is exponentially large. So the sample complexity to solve this problem from scratch is like a B to the L. So this is not good. However, if you do this kind of curriculum learnings, so first you run this stage, and then you train your model to choose this path instead of this path. Then so yeah, so okay, so then yeah, so then the next, so after you train your model, then next you go to the next step for here. Then in this local problem, then you want to train your model to choose this path instead of this one. In this local problem, the coverage is just a B, because you should choose just one of B choices. So the coverage is like a B in this local problem. So in each step, you should pay only B sample complexity. So then by sum up them for all depths, the required sample complexity is just L times B. So L times B is much better than the B to the L. Okay. So yeah, this particularly shows the benefit of the curriculum learning. Okay.
It sounds like so you solve local problems and just make a sequence of local problems.
Yes.
You can solve the global problem.
Exactly.
Is it really true?
Yeah.
We need exponential search because the problem is.
Yes. So yeah, so you need exponential search if you solve directly the entire problem from scratch. But if you decompose the problem into local problem, so then
you can't always find the right solution in the first layer.
Well,
you have to take the error.
So of course, okay. So there must be some error accumulations, but yeah, and we maybe in some so but here we assume that so then we can run each stage with very high precisions. Of course, it's not always true. So maybe in some situations. Yeah, this is a very much assumption. So
because as long as you have small error, then you need to search all the trees.
Exactly.
The complexity should be the same.
Yes, exactly. Yeah, but I think to reduce such accumulated errors, I think the curriculum running should be better. Yes. So instead of
Working practice?
yeah, so people usually consider like a easy to difficult like a strategy. So it's very common. Yeah, it is a very simplified version. So, yeah.
Given that you can measure the difficulty of the task properly.
Yeah, that's right. And also another assumption is that you can decompose the problem. So maybe in some situation the problem is very difficult to decompose. Like. Yeah, so maybe in the for example, in mathematics, it could be easy. It can be decomposed from elementary level school math to the junior high and the graduate school mathematics. But maybe in many situations, it's not obvious how to decompose the problem. So in that case, then you should pay this kind of sample complexity.
This graph, so I'm a bit confused now. So
Yeah.
are you solving one task?
Okay, it's an
intermediate goal to achieve a certain goal?
It is a bit confusing. So yeah, we assume that there are a bunch of the hierarchical problems. So there are different problems. So some problems you can stop here. So like please prove this theorem. Okay, please solve this please prove this lemma. So lemma is a short lemma. So then you can stop here. The next, you solve a little bit more difficult lemma, which includes lemma at this stage as a sub-problem. Then you increase the difficulty.
It's not a graph for a specific task, but it's an entire
entire problem. So there are a bunch of a series of problems. So yeah. So yeah.
So for me, it's similar to do some 3D search or pre-text search. Actually, you can also try some heuristics that you can have some A-star search.
Yeah.
Solution, right?
Yeah. So it's very related to like a search, so A-star search, or like a multiple tree search. So any search. So yeah, this is a this viewpoint is that to reduce the computation of such a search in the test time in post training. So by applying reinforcement learning of your model, then you can reduce the search space smaller, right, like this. So in the ideal case, the model we choose just one path. But this is a very extreme situations. But anyway, so yeah.
Yeah, I guess if you can propose some unmissable heuristics for this search, then you can quickly to find the solutions using A-star search and so on.
Right. So for example, in multi-color tree search, you should have like a prior distribution on the search space. So then that corresponds to this one. So you first train your model like this, then you have a good prior distribution on the search space. Then yes, so you put some more priority on the search space. Then you can reduce the complexity of the search. Yeah. Thank you for your comment. Yeah. So sorry, this was a very abstract setting. So so actually, the benefit of computation, the sample complexity can be shown for like a k-parity problem. So we have shown on more general settings, but I show just one situation, the k-parity problem. So suppose that you have an input x that is a uniform distribution on plus minus 1 to the d. Then there is some subset S. So subset S whose cardinality is k. Then you just take the product on this subset, okay, where xj is in a j is in S, and you take the product for all j in S. So then so this can be seen as a kind of logical problem. So you should enumerate xj1, xj2, and xjl. So then each step you pick up one coordinate and then enumerate, and then finally you report the product. So then that is the answer of this task. So now you decompose the k-parity problem to 2-parity problem, 3-parity problem, 4-parity problem. So you gradually increase the difficulty. Okay. So then if you do so, then curriculum runnings requires like a k times d square sample complexity with a gradient descent optimization guarantee. Okay. And so so I skip some details, but we consider just like a transformer model, and then suppose that so you do the gradient descent, you can run this k-parity problem with this sample complexity if you use curriculum runnings. But if you train this problem the K-parity problem from scratch, like without any curriculum learnings. So then you should pay d to the power k or something like that. So if k is like order d, so you should pay like exponential order sample complexity. So yeah. So this is it should be true. So like human beings, if you teach your kids, then you start from like elementary level math, then you gradually increase the level of the mathematics. But maybe you don't teach your kids from like a graduate school level text. So it's almost impossible. So then you should do. If you can decompose the problem, then curriculum learning helps. Yeah.
If I understood correctly, this K-parity problem is a kind of very special problem.
Yeah, very, very special.
For mathematical proofs.
Yeah.
So do you think like this special property contributed to like this bound? Or do you think the same kind of conclusion should hold in a more general case?
Yes, so in this paper, we consider more general settings. So this is just for explanation, just one example. So I believe so, yeah. This kind of an argument can be applied to more general settings. But this is a very extreme situation where the true path is only one. So, but in some situations, maybe the true path could be multiple. There are multiple correct paths. So in that case, then the discrepancy will not be that much.
As long as the multiplicity is constant. If it's exponential, you will support the exponential problem again.
Yes. Thank you. Yeah. And moreover, in some situations, maybe it's not like a very correct one, so that's like a more like a more it like a movement or something like that. So then it's not like a very just a discrete thing. So it can be more continuous one. Then maybe this bound will be a little bit different. But anyway, yeah. I think this argument can be applied to many more general settings. Okay, thank you. Okay, so maybe it's already 50. So maybe I skip this part. So what I showed in this part is like the transformer can do like can run like so-called induction head. So let us consider association recall, association copy. Okay. Currently your token is like U, then so the next token is a copy of the previous token that was in the same situation. Okay, I mean if your current token is U, then you should look back the same token in the previous token. Then the next token of this U was the correct one. Okay, for example, so this is called the trigger token. If the trigger token is Paris, then the output could be like an Eiffel Tower. So now you again observe the Paris here. Then you should answer the Eiffel Tower as a next token. So this is called associative recall. So yeah, what we could show is like the transformer can solve this problem. Yeah, but at some point maybe if the data distribution is not so good, so then it can overfit to the position. So just the transformer memorize the position of the trigger token. But if your data distribution has much varieties, then it can solve this problem properly. Yeah. But I skip some details here. But now, so I'm going to the next part. Okay, it is about the alternative architecture of the softmax attention. Okay, you know that the softmax attention is like a base component of transformers, but it requires like computation complexity order L square, where L is the context length. So this is not good. But instead, people consider like a linear method, like a state space model and a linear attention model. So if you use that, the complexity becomes like a linear to the context length L. Okay. Then the question is, so can we alter the softmax attention by linear attention in some situation? Okay. In what situations we can alter that? Okay. So so there are some candidates of linear models. So one is a linear attention, another one is a state space model, SSM. So linear attention can be written by like this. Okay. So the exponential of key transpose Q is this is a softmax. And this, so suppose that you replace this by like inner product of nonlinear features of key and Q. This is called the linear attentions. So by doing so, you can calculate the attention with linear computation complexity. So because you can compute this, like sequentially. So it will only require the linear computation. So another important example is a state space model. Okay? So in the state space model, you preserve the previous tokens information in a hidden state. Okay? Then you update the hidden state sequentially like this. Of course, there is the variance like a Mamba and so on, but basically the update looks like this. Okay? But anyway, so you only require order L computation. So there's linear computations. So that's good. So however, so there is a trade-off of the computation complexity and the performance. There is a trade-off. So actually, so there is like a negative result. If you use a single layer status space model, then such a single layer status space model cannot solve the associative copy that I explained in a previous slide. Okay, so the associative copy is like this. So okay, so if the current token is U, then you find a trigger token in the previous tokens, then you copy the next token of U to here. Okay, in this situation, the 7 is the correct answer. So the single layer SSM cannot solve this. So yeah, this shows, particularly shows the limitation of status space model. But however, in our paper, we showed that if you increase the layers, like 2 or 3, then the SSM can solve this. So if you combine the SSM and the fully connected neural network, so then the multi-layer SSM, like it's not extremely deep, like 2 or 3 layers is enough. Then they can solve this kind of problem. So this is because by inserting some internal layers, then with fully connected neural networks, then you can compute some importance of each tokens. Then you can pick up the some token information from the sequence. So that's a key, key observation here. And also, in addition to this very simple problems, so we can show that SSM can estimate so-called piecewise gamma smooth function. It is a highly nonlinear function on the sequence. Then with almost the same performance with transformers. So if you pay a little bit more layers, then SSM can alter the softmax attention in some situation like this. Yeah. So, but of course, you should pay like a constant times larger number of parameters. So maybe depending on the situations, so maybe softmax is better. Yeah, but yes, it is a like trade-off. Okay. Okay. So next, I want to consider the linear attentions. Okay. So in the linear attentions, so remember that which was given like this. So the softmax attention was given by like exponential of key transpose y. So then from like a Bochner integral theories, this can be written by the expectation of the product of nonlinear features, where phi xz is given by like this. So yeah, basically you are using just a Bochner integral of Gaussian kernel function. Yeah. So if you approximate this expectation by finite sum, then you obtain a linear attention like this. Where so here phi x is a nonlinear feature map from x, then each ith element of phi x is given by like this. Yeah. So this is a feature map of this one. So yeah, just a finite sum so that you can approximate these expectations. Then the question is how many features you need here. So of course, if you have infinitely many features, then you can simulate this expectation. Then, but the question is, so how large a feature should be? Okay. So then what we've shown in this paper is, in this new paper, is that if the number of feature n is greater than the so-called degrees of freedom, which is defined by this quantity, then it is enough. So then in degrees of freedom, there is like a covariance operator, sigma k, which is given by like this. So in the definition, so there is information about distribution of x, like a distribution of tokens. So yeah, so this bound is like a distribution dependent, data distribution dependent bound. Okay, so yeah, and so like then after that you just okay, so after you determine the number of features, then you can distill the information of the softmax attention to the linear attentions. Yeah, so by minimizing the cross entropy between the softmax attention and linear attentions. Okay, so the good point is that we can do it in a layer-wise manner. So yeah, so you can parallelize these distributions. Okay, so you applied this method to some existing real data set and real practical models. Then we found that for the lower layer, so lower layers, so you need many features. But in the deeper layer, so in the later layer, you don't need many features. So this means that in the lower layers, so the transformer is doing very complicated information processing. So you need very high dimensional features. But in the deeper layer, the transformer has already finished some information processing, so you don't need much features. Yeah. And also we compared with like fixed dimension method. Okay, so you fix the number of parameters, number of features on all layers. You use the same number of features here. Then we observe that by changing the number of features, depending on each layers, you get a better result. Okay, and comparing with some existing methods, so we have a better, better performance. Okay, so yeah, that's it. So yeah, thank you very much. So if you have questions, I want to take. Yeah, thank you very much. Maybe I got too many questions.
Let's ask a quick question. I think the technical parts are quite high level, and we couldn't really follow the details. But in high level, so what kind of messages did you obtain so far?
Okay, so it differs depending on each section. So the first one is it's better to use curriculum learning. So then, as long as you can decompose the problem, so it's better to use curriculum. So then the problem, maybe the next question could be to how to find the appropriate difficulty. Okay, so for for example, you are given some transformer now. Then what is the next input? So what should be the next?
So the assumption is you can chop the problem into small pieces easily. Then also you can evaluate how difficult each small task is.
Yeah. So that's the assumption. So in practice, how to do that could be like a important next question. Yeah. So and here, so yes, and maybe here, so SSM has some potential to replace the softmax attentions, but
in terms of computation,
in terms of performance, but you should pay more. Maybe in some situation, maybe you should pay more number of parameters. So it's not like there's no free lunch. So there is some trade-off. Yeah, maybe if you use a status space model, like test time computation could be faster in terms of the context length, but maybe you need more layers. So yeah, but we don't have a very exact answers or how to solve this. But anyway, there must be some trade-off. Yeah.
Thank you. So that's very interesting.
Yeah, of course, please.
Thank you for the talk. I'm interested in the curriculum learning part. Okay. You have mentioned that the curriculum learning is already used in practice in some products.
Yeah. So as far as I understand, so for example, like a DeepSeek or the QN, so for training that, so they say that, so they do the reinforcement learning. Then from like easy to difficult. But I don't know some details, but yeah.
Okay, but yeah. I feel that if so, then the performance is not as good as like a prompt engineering by human beings, because sometimes I feel that I should do that for foundation models rather than let them do it themselves. Because if they use curriculum learning to decompose the difficult problem into some easier problems, it's not a very effective. The answers are still incorrect. And I'm mainly using GPT-5 and DeepSeek, and I feel that I need to prompt them with easier task, and then I need to guide them.
I see. Okay.
Yeah.
I see. Okay. Okay. So you should guide. Yeah. Okay. well, yeah. Okay, maybe that could be a little bit different from like a prompting. Like I mean, well, the model is too much got used to the situation where the human beings give some goal. So okay, so please answer this question. So then we choose the level of the difficulty. So yeah, in the curriculum learnings we do that. So we choose the difficulty. So then there is the correct answers. So maybe they are not well trained to do that curriculum learning by themselves. So
but they should do that.
They should that, yeah. So
like from my own experience, I first asked a difficult question, and I found that they cannot solve it. Then I will try to guide them through, please prove this lemma and this more difficult lemma. Then finally the theorem. Then they can really do it. But if I directly ask the final question, they cannot really perform curriculum. I don't know why.
Right. I agree.
Okay.
So yeah, well, in that sense, maybe the transformer should do like a kind of active learning in context settings. So yeah, but it could be like some different task. Yeah.
Okay.
So but it's a very interesting problem. Yeah.
Okay. Thank you.
I was just curious whether there's a relationship with hierarchical reinforcement learning. But I think in hierarchical reinforcement learning is instead of really being sequential, I guess is more a view of having finer and finer controls, starting with a kind of, so it's more of kind of increasing the space. But I think in this case, you gave the example with math. I mean, you could see it this way, that an easy problem is a very guided problem, and then you kind of remove the rails, and so it's more of a kind of zooming in, or kind of, leaving more and more degrees of freedom, right?
I think it's a different one. Yeah, so in terms, so like instead of just looking at more like a fine resolutions, instead of increasing the resolutions, it's more like you decompose the sequences. So like if you consider this movement, so then you decompose the goal into the small pieces, goal 1, goal 2, goal 3. So then maybe hierarchical reinforcement learning sounds like, I'm not very familiar with hierarchical reinforcement learning. It looks like to achieve this goal, then maybe there is like a very outline. So first you get like a outline of the trajectory, then you go into the more details. So how much torque do you need? So like down like this. So yeah, it's like a different direction.
So it's really sequential in your case.
Yeah, it's more. So yes, it's actually it's more sequential things. Yeah. Okay. But maybe the same argument can be extended to that situation. But I should consider that. Yeah.
Because in the math example, you can start with easy assumptions. You will reach the same goal, but it will be a lot easier. And as you remove the assumptions, it might get harder and harder to reach the same goal, and there will be kind of more of a finer control.
I see.
So I guess there could be the two viewpoints, right?
You're right. Yeah, that's a good point. Yeah. So yeah, I understand. Yeah, thank you. Yeah. Okay. So then maybe I should finish now. So thank you very much.
I'm Atsushi Nitanda from A*SHIFA and NTU. So today I'll talk about the statistical analysis of the Sinkhorn iteration for Schrödinger bridge problems. So Schrödinger bridge has been studied in the context of the physics, stochastic differential equation, stochastic control, and the optimal transport. In the machine learning context, so it can be considered as a data generation method, like variational autoencoder, generative adversary network, and the diffusion model. All of them can generate an output from the noise distribution, such as Gaussian noise distributions. So among them, so especially the diffusion model can be considered as the state-of-the-art data generation method from Gaussian noise. So Schrödinger bridge is highly related to the diffusion model. So let me briefly introduce what's the diffusion model. So we are first given target data distribution like this, so like the image data set. So then diffusion model consists of forward and backward process. So in the forward process, we just perform the random perturbation from the input data distribution. So just by adding Gaussian noise at every time step. And eventually, we arrive at the Gaussian distribution by the Brownian motion effect. So then we trace back this process by the reward process, so like this. So the noticeable property of diffusion model is that so backward process shares the same marginal distribution with the forward process, and then we can recover the input distribution. So because of these properties. So yeah, this is a data generation process in the diffusion model. Also, another important image generation task is unpaired data translation. For instance, in the case of the image dataset, so this is like the image translation from female to male like this. So maybe, so cycle GAN is the original unpaired data translation which first achieved the high performance. So then for this kind of the data translation, so we expect that this translation preserves some contents of the data, so in some sense. So this property reminds me of the optimal transport. So let's say we want to transport a bunch of the points obtained from source distribution mu to the target distribution nu. So we would like to minimize the transportation cost to transport input distribution to the target distribution. Actually, so optimal transport gives us such most efficient transport plan. The problem is formalized like this. So pi is the coupling distribution given input and the target distributions mu and nu. So this is just a joint distribution defined over the product space of source and target species. There is a constraints like the marginal constraints. So marginal of pi over source space must coincide with the source distribution mu, and the marginal over the target space coincides with the target distribution nu. So given this condition, we minimize this transportation cost achieved by the current transport plan pi. So this is the optimal transport. So let me intuitively compare non-optimal and optimal transport plan like this. The left one is the non-optimal one, and the right is the optimal one in the Euclidean sense. In the case of the non-optimal coupling, so clearly, it's non-efficient. Both source and target distribution have two modes, upper mode and the bottom mode. So then transport plan close like this. It's clearly non-efficient in the sense of the Euclidean cost. But so looking at the optimal one, so intuitively, it's a best transportation plan because it's almost the horizontal transport, so which minimizes the cost in terms of the Euclidean. So then we can expect, this transportation preserves some contents of the input data if these data is distributed in the semantic spaces. So in some sense, yeah, well-designed semantic space, latent space. So actually, Schrödinger bridge inherits both properties of optimal transport and the diffusion models. So the key difference from the diffusion model is like this. So in the diffusion model, as I said, so basically the diffusion model translates the Gaussian distribution to the target distribution. On the other hand, Schrödinger bridge can connect any given two distribution. So input and the target distribution can be arbitrary. Also, another difference is that, so in the diffusion model, so we need to consider infinite time horizon. But on the other hand, Schrödinger bridge can perform on finite time length. Also, Schrödinger bridge is known as an approximation to the optimal transport. And so because of this property, so Schrödinger bridge can be applicable naturally to data translation tasks like male to female, child to adult, so something like that. Okay, so let me briefly introduce the problem setting of the Schrödinger bridge. So we first have source and target distribution mu and nu like this, and then the objective function is like this. So here, So P is the path distribution. So that's the probability distribution defined over the path space. In other words, so this distribution P can generate a random path from mu to nu, so because of these constraints. So there is a constraints, so marginal constraints on the initial point and the terminal point. So they must coincide with the input source distribution and the target distribution, mu and nu, respectively. So given these constraints, we would like to minimize the divergence between the current path measure P and the winner process. It's just a random process, unpredictable random process, like the Brownian motions. So because of this objective, so Schrödinger bridge forces the obtained path measure P star to be close to the kind of the optimal transport. Actually, so it's known that Schrödinger bridge can be equivalent to entropic regularized optimal transport like this. So here is so looking at this objective function, the first term corresponds to the optimal transport, the pure optimal transport. So she is the cost function, so Euclidean distance between x and y. And we also have additional regularization term, K divergence between the current coupling pi and the product of source and target distribution. So then, so this additional regularization makes the problem easier to solve in general because this K divergence is kind of the strongly convex functional in the space of distributions. So here P star infinity infinity stands for the optimal path measure, so which solves the Schrödinger bridge problem, so introduced in this slide. And pi star is the optimal coupling for this EOT problem, entropic OT problems. So then, so between them, this kind of relationships holds. So actually, the given optimal coupling pi, the optimal Schrödinger bridge is a mixture of the Brownian bridge, so like this. So given some point x0, x1 obtained from the optimal coupling pi star, so P star is a mixture of the Brownian bridge, so like the random perturbation starting from x0 to x1. So then, so mixing this process, we get the optimal Schrödinger bridge. So on the other hand, given optimal Schrödinger bridge P star, so we can decompose it into this form. So then we get the optimal transport plan. So this means the Schrödinger bridge and optimal EOT are mathematically equivalent. So this is a nice property, and that's why so Schrödinger bridge can perform like the diffusion model and the EOT.
So I'm not quite familiar with this one. So optimal transport is more like a one-step transformation.
Yes, yes.
But the Schrödinger bridge is more like a path. You gradually change the distribution.
Yes, so Schrödinger bridge is actually a stochastic process. So continuously transport the input data to the target, but by projecting to the marginal, so considering the marginal distribution. So then, so which gives us a transport plan like the OT. So just projecting the distribution at the initial and the terminal point to source and target space.
In that case, how the path is determined? Because you only cared for some transport.
Yes. So okay. So on the other hand, so let's say we are given the optimal transport plan, so which joint distribution defined over these two marginals. So then, so let's say we get two samples from the source and the target. So then we can connect them by Brownian motion, so Brownian bridge. So then mixing these process, so with respect to all combinations. So then we recover the Schrödinger bridge solutions.
But this sounds like Schrödinger bridge is more complex than optimal transport. But you said they are equivalent.
Yeah, mathematically equivalent because so now, so given Schrödinger bridge solution P star, so we can write this solution as like this. So basically, so Schrödinger bridge is determined by the optimal transport plan. So then, using this optimal transport plan, so we just mix the Brownian bridge.
Thank you.
Yeah. Yeah, anyway, so this is property of the Schrödinger bridge. In other words, so Schrödinger bridge is EOT problem. So then, given population distribution mu and nu, our goal is to obtain the optimal Schrödinger bridge P star infinity infinity. So this infinity stands for the population distributions. But in practice, we are only given finite observations x1 to xn from source distribution mu and y1 blah 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 yn from the target distribution nu. So then our task is to construct an estimator PMNK to approximate the true Schrödinger bridge P star infinity. This is our task. So here, so in order to obtain the estimator, we basically perform iterative algorithms. So then this K stands for the number of iterations. So that means we care about the convergence of the algorithm as well as the statistical error. So our goal is to estimate the TV distance between the true Schrödinger bridge P infinity star and the estimator PMNK. So yeah. So then we further decompose this TV norm into sum of statistical error part and the algorithmic error part. So we care about both terms. Okay?
So sorry, I have a question. Here the P star is for population distribution, but you given the empirical observation, how you evaluate the generalizing error?
Yeah, so I didn't yet explain what's the PMNK. So this is actually estimator. So from the finite observation x1, xm, and yi. So yeah, I'll explain it later.
Okay.
Yeah. So then, so we can construct some estimator, and we would like to evaluate the gap. Okay. So also, our research is motivated by the fact called minimum intrinsic dimension scaling. So recently reported by Strum. So according to the manifold hypothesis, so we believe the data distribution lie on lower dimensional space like this, so the torus in the Euclidean space, and then so machine learning method can exploit this kind of the structure, so lower dimensional manifold structures. Actually, in the context of the EOT, so the previous work, Strum, reported these properties called minimum dimension scaling. So the convergence rate of EOT can be fully governed by the minimum of the intrinsic dimensionality of source and the target distributions. That means even if the dimensionality of source distribution is quite high, so it doesn't matter. So the convergence rate, statistical error bound, is fully captured by the lower dimension property of the target distributions. It's a MID scaling. So more precisely, so this work, so Strum 2023, so obtained this kind of the convergence rate. So here I didn't explain effort, so but yeah, it's just a EOT solution in the dual space, and the L2 gap between the estimator obtained by EOT and the true solution can be upper bounded by like this. And the dependence on the dimension is actually intrinsic dimension d nu. It's a manifold dimension of the target distributions. Okay? So our work is motivated by this fact. Okay, so next, so relating to your question, so I'd like to introduce our target algorithms. So we would like to analyze the property of the EOT method called Sinkhorn bridge, recently proposed by this work. So yeah, in order to explain what's these algorithms, so let me briefly mention the dual formulation of EOT. So this is a EOT problem. It's a primal problems. And we also have dual problem formulation like this. So this problem can be simply obtained by just taking the min-max of the Lagrangian associated with this primal problem. So here F and G are variables of this problem called Schrödinger potential or dual potential. Then, so the optimal condition of this dual problem is like this. So F star can be described so by log some exponential of something like this, and vice versa. So actually, so this is very strong constraints like the inductive bias. So because of this property, so EOT problem has a nicer property in terms of the generalizations. Actually, F can be perfectly captured by G star and the vice versa. This is very strong constraints in general. Also, yeah, this is population settings. So, but what we perform, so what we solve is the empirical EOT actually. That means we replace the problem by, we rewrite the problem just by replacing population distribution mu and nu into the empirical distribution mu m and nu n like this. So then, so in the Sinkhorn bridge, it's an estimator for Schrödinger bridge. So we solve this problem. And the corresponding optimality condition for this empirical problem is like this. This is just a replacement of the previous one. Okay?
Are the two epsilon the same one?
Sorry? Two epsilon?
The epsilon, the regularization parameter.
Ah, yes, same as so regularization parameter. Yes.
Okay, so in practice, should that one be a very small value or relatively large value?
Yes. So, but yeah, so that depends on what's the final task. Actually,
Okay.
so yeah.
Yeah, because
So-
I thought originally you have a hard constraint, but you put the hard constraint into the entropy regularization.
Yes.
So epsilon should be a hyperparameter. You need to tune it.
Yes. Yeah, I understand. But yeah, actually, so it depends on the final task. So if our task is finally obtain the pure optimal transport for population distribution, so then we need to care about the choice of epsilon. Actually, the final task is recovering the pure optimal transport, non-entropic OT. But so in this talk, so I don't consider such a recovering of the pure optimal transport. So we just care about the recovering of the EOT solution for population distribution. Actually, it's very well aligned with the existing results. Okay, so
because my concern is that if epsilon is very small, then 1 over epsilon can be very large, right?
epsilon.
Yeah, if because in many cases the regularization parameter is a very small value. So
Yeah.
1 over epsilon can be very large.
But yeah, it's not necessarily true. So if we look at the image generation task, so for actually in the diffusion model, so noise perturbation is clearly, so empirically important. So basically, so this epsilon has the same role as the volatility of the diffusion model.
Okay.
So if we let epsilon to 0, maybe so the Schrödinger bridge never generalized to the population distribution because basically it leads us to the empirical point.
Okay.
So if we directly solve the OT, so actually if our target is to obtain the true optimal transport for population distribution, so we have to construct some algorithms to get an estimator for the population OT.
Okay.
But yeah, in order to achieve that, so we need some regularization in general.
Yeah, and if epsilon is not very small, that means the regularization is very strong.
Strong, yes.
Okay, thank you.
Yes, but yeah, our task is just recover the EOT solution for population distribution. We don't care about the trade-off coming from epsilon. Yeah.
Sorry, just clarification. So, because here, I mean, you talk about Sinkhorn bridge, but on the next slides, I mean, this is the standard Sinkhorn algorithm, right? The kind of entropy regularized optimal transport, right?
Yes.
So here there's no, at the moment, there's no bridge part, right?
Yes, I'll explain it
Okay.
in the next slide.
Okay.
Yeah.
And second clarification. So, is it So of course, I mean, initially these kind of optimal transport params where this kind of dot moving param, right? You really want to take the shortest path, right? But so in many params, I mean, people have worked with just transports that are not necessarily optimal as long as you're transporting one measure to the other. And you're not really paying much of a cost for not taking the optimal path, and so then you can leverage other properties. Is that really a concern here of optimality?
Yes. So we target image translation task like the male to female. So we have to care the shortest path. So in the latent space of the some data generation model. Actually, so let's say this is a male distribution and the female distribution. So hopefully we expect this kind of the horizontal transport preserves the appearance of the face. So then if some autoencoder model can efficiently extract such property. So it's just an assumption. Anyway, so our work is motivated by minimum intrinsic dimension scaling. So it's a very nice property of EOT. So so because of the EOT structure, so EOT enjoys this property. So the generalization performance is fully captured by the lower dimensional structure. It's also one contribution of EOT. Anyway, so I introduced the Sinkhorn iterations. So like this, so in order to solve this empirical EOT, we perform Sinkhorn iteration. This is basically alternating maximization method. We just perform gradient ascent for this problem alternatively with respect to f and g. And then the convergence of this Sinkhorn is well known, so like this. So this exponentially, this converge with the exponential convergence rate like this with respect to Hilbert metric. So here I'd like to explain what's the Sinkhorn bridge. But before that, so I need to introduce the SDE formulation of the Schrödinger bridge. So given true Schrödinger bridge P star, so we would like to construct SDE formulation using the drift function B star. So B star is the drift function which defines this path distribution P star. And this drift function can be written in this form. So basically, so given current point xt and time step t, the drift function, so which defines the direction of each particle xt, can be written in this way. So this is the difference between this point and xt. And this point is the weighted sum of the target point y obtained from the target distribution nu, and the weight is the softmax. Okay? And then, so our task is to approximate this true drift function corresponding to the population distribution. So it's obtained by just replacing this distribution to empirical one and replacing this dual solution to the empirical solutions like this. So this is our estimator which approximates the true drift function. So actually, even though the potential function, potential function is defined over the empirical distribution. So this drift function can be defined over a whole space of X because the input xt only appear in this term, so Euclidean space. So we can define this drift function over entire space. Then we perform, so we simulate this stochastic differential equation starting from the true population. Actually, when evaluating the test performance, so we can get a sample from the true population distribution. But the drift function is fully obtained by the training dataset. Okay, so then we can construct an estimated Schrödinger bridge PMNK, which approximates the true Schrödinger bridge. So K represents the number of Sinkhorn iterations, and then so this potential function GMNK is obtained by K's iteration of the Sinkhorn. Okay, this is our estimator. So then we would like to evaluate the statistical capability of this PMNK. Okay. Okay, so maybe I consume a lot of time. So okay, anyway. So yeah, so here we make two assumptions to get convergence results. So first one, both are related to the support of the data distribution. Why is like that? So we suppose support of input and the target distribution mu and nu are contained in the ball with radius capital R. It's a bounded distributions. So also another assumption is the data manifold hypothesis. Actually, we suppose the support of data distribution nu is a compact Riemannian manifold embedded into the Euclidean space. So this is a important assumption. And we basically suppose the dimensionality of this Riemannian manifold is lower than the ambient space D. And the dimensionality is written by D nu. Okay, so then let me introduce the existing bound under the same conditions. So actually, so this is a paper proposed the Sinkhorn bridge. And then they also obtained some convergence result. So like this. So given the empirical target distribution and the true source distribution mu, so they established this kind of the upper bound. So like this. So important point is that actually the right-hand side upper bound so only depends on the intrinsic dimensionality regarding the dimensionality. So it's a kind of the dimensionality scaling. However, the limitation of this result is that so this result supposes the full knowledge of source distribution mu. That means in order to get this estimator, so we have to consume the full knowledge of the source distributions. So this means this limits the applicability to the real setting. So basically, this result is only applicable to very simple distribution, like the Gaussian or something like that. So then, in order to extend this result to fully discretize the setting, so we exploit some sophisticated approaches, so obtained in some results. Okay, anyway, so before explaining some technical details, let me briefly introduce the final result obtained. So given empirical distribution mu m and nu n, so we established this kind of the upper bound between true Schrödinger bridge and the estimator by the Sinkhorn bridge. The upper bound is like this. So the first remarkable improvement is the convergence rate in the number of observations from the source and the target distribution m and n. So actually, the previous result was slower, so like square root n. But actually, this is actually slow given the recent result obtained in the context of the EOT. And then by leveraging the latest result in the EOT, so we successfully improved the convergence rate in the sense of the number of observations. Also, the next point is that, so this regarding the dimensionality of the data distribution. So basically, so this d nu dominates the bound. And d nu is the dimensionality of the lower dimensional Riemannian manifold. So that means this upper bound is basically captured by the dimensionality of the Riemannian manifold. But so there is so I paid additional cost. So unfortunately, so this bound does not perfectly avoid the dependence on ambient space. Actually, we have additional term d so as a coefficient. However, the dependence is quite mild. It's just a linear dependence on d. So yeah, anyway, so this is a result obtained in our work. Also, we empirically verify this result at each time snap. So t equals 0.1, 0.3, blah, 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 0.9. So then this color represents the error from the true Schrödinger bridge at some time snap. So, and we notice, so basically the error mostly comes from the point near the terminal point. So yeah, this is because, so basically, because of the nature of the Schrödinger drift function, So basically, so because of this formulation, so the empirical data point pulls the particle xt to the empirical point, the training point. So that means Schrödinger bridge cannot generalize at the terminal point t equals 1 because the all paths will converge to some point of the training data set. So then we need to perform early stopping before reaching the terminal point. So that's the same case in the diffusion model. So the diffusion model has also same problem. So we need to perform early stopping before reaching the terminal point. So then,
does any regularization help?
I'm not sure. So actually, so noise perturbation is one approach, but yeah, I don't know it's fully recover such issues. But anyway, so in the diffusion model, so we practically perform early stopping. So that's why we have this notation tau. So this limits the time range to tau less than 1. And actually, so by letting tau to 1, so this term blow up. So this doesn't generalize. So we need to perform early stopping. Okay. So now, I wanted to explain a bit about the proof techniques, but yeah, I already consumed. Yeah, I ran out of the time, so I have to stop here. So yeah, thank you.
Yeah, thank you for the talk. So for entropy regularized optimal transport, we solve for M, F and G, right? FMN and GMN. And in this case of Schrödinger bridge case, so the Sinkhorn bridge, it seems we solve for BMN and GMN, right? So we replace F with B. Mm-hmm. And so is that correct? And
yes, so yeah. Yeah, in the empirical setting, so we perform Sinkhorn iterations and we approximate FMN.
And is it not equivalent in that sense? Is there like a benefit to solving Sinkhorn bridge as opposed to, let's say, EOT?
Yes, so yeah. The motivation behind the Sinkhorn bridge is that so we also have SDE formulation like this. So this is a true Schrödinger bridge defined by B infinity. So B infinity is defined by the true potential G infinity for population distribution. So if we can perform the Sinkhorn iteration for population distribution mu and nu, so we can directly compute this one. But yeah, it's impossible in practice because we cannot handle the population distribution in general. So instead, we perform Sinkhorn iteration for empirical distribution. Then, so we get GMN. So this is just a replacement of G infinity with GMN. So then, using this drift function, so we can simulate the approximated SDE to the true SDE. So this is the mechanism behind the Sinkhorn bridge. So does it make sense?
But would solving this be different from solving the entropy regularized OT?
Yes. Basically, yeah, same. If we perform the projection to the initial and the end terminal, so then we recover EOT solutions.
So theoretically they are the same, but in practice it could be different, right?
Sorry. So more precisely, so actually, in this setting, so we start this distribution from the true data distribution mu instead of the empirical point. So then we cannot recover the EOT solution for empirical distribution because the start point is already different. So, but yeah, in order to ensure the generalization, we need to start from mu. So this is a bit difference.
Okay, thank you.
We have a question from online. So the question is like, it might be nonsense theoretically, but does it make any sense to independently set different values for the regularization parameter epsilon of the marginal EOT and the epsilon of the Brownian bridges W epsilon used in the mixture? So you use a different value.
So that means we use different value of epsilon in training and test.
Maybe, yeah, maybe. I think so.
I don't have any idea, sorry.
Other question? Okay, No. So then, please thank the speaker again.
Thanks for the introduction. Good morning, everyone. I'm Haiyan from C5A*. Today, I'm going to talk about some of the recent agentic code generation frameworks we have developed at C5A* for some robotics and cognitive agent domains. So agentic AI is like making the AI agents autonomous. It's like the translating the AI from solving closed domain problems into solve some open domain problems. So we'll see a lot of important applications like robotics agents and general purpose agent LM assistants. So among these agents, actually code generation is the fundamental capability that can make the AI agents truly autonomous, because like once the AI agents can program, then the AI agents can like write the improve the prompt for itself, like do the planning, invoke different function calls, and like make the autonomy really happen in our real life. So, however, like agentic AI, like in real world, is really challenging. Like one of the fundamental challenges is that like it's about this long horizon fragility in our real open world problem, especially open world problems. We have some long horizon problems, but like small errors can amplify over time, and the agent all frequently fail. For example, the left example is like a Boston Dynamics Atlas robot. It failed at a made demo during when it's like carrying a box around. And also we know that LM reasoning is also challenging when the decision horizon can be longer. Like the single turn reasoning under a fully specified settings, like the LM is pretty good at it. But when we change into the like multi-turn like reasoning, the LM suffer at large drops in aptitude, and there's a sharp increase in unreliability. So apart from this long horizon challenge, actually another problem is the adaptivity of agentic AI. So how to make the AI agent continuously improve in the environment, like it's another bottleneck. For example, if the agent is lacking this kind of self-improvement capability, when the agent fails, it can be very hard to get back. And there's another example that like in this Gemini agent just accidentally wiped out all the user data like drastically because of like this accumulation of small errors. So the problem is how can we simultaneously address this problem of long horizon and self-improvement? So I think one of the promising solutions is that it's this agentic workflow, because workflow can decompose the long horizon problems into modular sub-problems. And also like agentic workflow is about using an LLM to automatically like optimize its own workflow solutions, you know, like, the problem of agentic workflow, it can be considered as a code generation problem. Basically, we represent the workflow as a symbolic graph, and we let the LLM to automatically generate a piece of executable workflow code. So here, like in this symbolic graph, the node represents some symbolic LLM invoking functions, like performing some specific operations. For example, if we want to build up a workflow for solving a math problem, then like the nodes can represent some specific symbolic functions about playing some particular roles like solver, evaluator, and tester. And the edges capture the logic and the data and control flow between these LLM invoking function calls. So when we want to optimize this workflow, we use the LLM planner to automatically generate like the workflows represented in the code, which is often like we represent the workflow in the Python programming language, and then like this code generation can perform iteratively, and the LLM can receive some feedback and like iteratively optimize its workflow structures. So we have developed some system called Mermaid Flow. So Mermaid Flow is a system that is like bridging the idea of agentic workflow with some graph-based workflow representations. So we know that if we generate the workflow in the Python. Like workflow, although it is itself is essentially a symbolic graph, but Python is a script language, so it's very hard to let the LLM agent to interpret the node connections and edge connections with the Python language, and also have a lot of hallucination problems. But if we represent the workflow in the graph language, then it will be, the syntax will be clearer and it will be more robust. So Mermaid flow is like using Mermaid, which is a domain-specific graph-level domain-specific language to represent the agentic workflow and let the system automatically optimize this Mermaid-based agentic workflow representation. So there are several key benefits about this using a Mermaid to represent the agentic workflow. So Mermaid is a language that widely used in the industry to visualize the flowchart and the industry workflow graphs. So it provides graphical visualizations for it's very convenient with graphical visualizations for the Mermaid-based workflow code. So if we shift from the Python-based into a Mermaid-based workflow systems, then the Mermaid also provide us with a built-in graph compiler for us to verify whether each of the workflows generated by the LLM is a valid workflow or not. So also Mermaid is supported by receivers, supported by multiple platforms. For example, when we use the GitHub or Notions, and the Mermaid code can be immediately visualizable in those platforms. So it makes planning and do this workflow optimization with Mermaid super convenient. So, in agentic workflow, actually, we are using LLM to search at the symbolic graph space, best graph structures that can solve this problem. So essentially, in order to improve the diversity of the workflow, and so we also provide the Mermaid flow with some evolutionary functionalities. We define some workflows evolutionary operators to evolve the structure of the workflow to generate some meaningful alternative structures and improve the search space quantities. And also, another important thing, feature for Mermaid flow is that we can, within Mermaid flow, we can guarantee that every workflow generated is a valid one. So, so that when we are searching through the search space defined by the Mermaid flow generated workflow graph, then each candidate is valid. So the search can, we can significantly enhance the search quality. So here's an example, a Mermaid flow can conveniently swap some, perform the evolutionary operators. We can merge the head of the workflow 5 and the tail of the workflow 4 to form a new workflow 8, which is essentially an ensemble agent with a test module. The right side shows a piece of Python code. This side is essentially comparing the Mermaid with Python. We see if we represent the workflow in a Python, then its graph level structures is also often hidden in this script code. But if we represent it in the Mermaid, then the graph level syntax makes everything very clear, and LLM becomes more robust to generate this Mermaid-based workflow. Mermaid flow can robustly optimize the workflow representation because every candidate it generates and searched is a valid one. So compared with some Python-based Python-based workflow optimization method, which is a flow, so Mermaid flow can continuously improve even at the later stage. So we can see the A flow's best workflow is generated by its 5th optimization iteration, but Mermaid flow can continuously improve, and its best workflow structure, it can be discovered even after the 20 iteration budget. And also it scores the highest across the 4 reasoning benchmarks. So based on this Mermaid flow, we have developed a series of agentic workflow systems across different domains. So this flow searcher is essentially integrating some empowering Mermaid flow with some experience-driven memory RAG algorithm to do some open domain web search. So we know that currently major web search agent, there are fall into this React framework. React framework is like agent is agent is doing the web search in a linear manner. So once the search fails, it will repeatedly run the same prompt, like it's performing a linear process to solve the problem. But like a flow searcher is like integrating the idea of agentic workflow into this web search. So instead of using a fixed prompt to solve the problem, we decompose the problem into subquery, and we generate a customized agentic workflow to solve each of the subquery. So essentially, this is the decision-making hierarchy for flow searcher. So Q is the original queries. We decomposed into we decompose Q into a series of subqueries mu I, and each subquery will be mapped into an agentic workflow, which is represented by GI, and the GI will be executed by some like modular actions of alpha and omega. So at the low level, if we flow searcher enables like continuous decomposition at the low level. So essentially, this is not only a two-level hierarchies, and the agent can search deeper when the problem is more complex. So this is shifting the conventional like React-based system into a truly deliberative searching agent. So flow searcher can also like leverage can also make the agentic workflow to learn from the experience, because it connects with some memory-based system. So in this flow searcher, we construct a 3-level memory. So at the task level, we save all the queries and the subqueries decomposed. And at the graph level, we save each of the agentic workflows, like structures for each of the subquery. And at the node level, we save each of the execution traces. So this 3-level memory provide a rich experience of past like successful and failure experiences, can offer us valuable insights in when we are solving the new queries. So we formulated some universal compositional retriever, which can conveniently retrieve experience across these 3 levels. So when we are planning a new agentic workflow and generating its prompt, we can retrieve the insight from this retrieved memory and optimize the workflow. So a key insight of flow searcher is that our agentic workflow-based system is purely training-free, but most of the current mainstream open domain web search agents, they are mostly relying on RLHF to improve the performance. So we compare our flow searcher with Web Thinker and Web Dancer, where both are very recent works from NeurIPS 2025. So flow searcher can significantly outperform these RLHF-based web search agents. So this means that a flow searcher is trying to optimize the structure of how to solve the problem instead of what data is needed to fine-tune the model. So this kind of structural flexibility leaves us a great potential to improve the performance of the open domain web search agent. So it also highlight a pivot way for learning from experience can provide us with valuable experience to improve the problem. So apart from this open domain search agent, we also use the Mermaid flow on some different applications. So Prev agent flow is it's a system that we use Mermaid flow to improve the privacy preservation for this web agent. So this example here shows web shopping agent. So web shopping agent is the agent that is purely driven by LLM that is performing some shopping just like human do. So the agent is search some items from the shopping list and add it into the cart and perform the shopping. So in this kind of web agent, it will access a lot of personal user data. So privacy preservation become especially important. And in our work, we consider protecting the personality identifiable information, PII, which are we want to develop an agentic workflow to simultaneously solve this web agent task and also protect the PII from leaking to the web or to the LLM API. So in this private agent flow, it's also adhering to the decomposition and the privacy preserving principle. So basically, given a user query, we decompose the user query into sub-steps. So this decomposed steps is managed in a way that at each sub-query levels, we perform the privacy preservations. So the optimization objective is that we want to optimize the task utility while minimizing the privacy leakage to the web and the LLM API. So in this private agent flow, we schedule, we plan a workflow and execute this workflow in a step-by-step manner. And within each node, we do the privacy-aware data handling. Basically, for each node, we will identify which is the privacy levels, and we assign the privacy policies based on this dedicated privacy classifications. And also this framework is extremely flexible in a way that we can flexibly configure the system level privacy policy, what will happen if we identify some high privacy. So this kind of mapping is very flexible to be handled by this agentic workflow system. So private agent flow is compared with some purely LLM-based non-workflow system called AgentDAM. This is a work from Meta Gen AI team, also published in Europe 2025. So we can see that our workflow-based system can simultaneously enhance the task utility and also significantly lower the privacy leakage. So apart from this agentic workflow optimization, we also use workflow on some embodied robotics control problems. So this instruct flow is that we use the workflow to formulate some symbolic constraint induction pipeline to let the robot to generate more responsible code. So in this instruct flow, actually the task is that given a task, we want to use LLM to generate a piece of executable Python code to directly solve this task. So the problem is that when we send this Python code into execution, the agent often encounters some failures. So how to learn from these failures is the key problem. So in this instruct flow, actually we use the instruct flow planner to plan instruction as a graph. In this graph, there are two types of nodes. One is the action node, which one is the planning node, which determines what to do next, and the other is reasoning node, which determines how to choose the objects, how to reasoning on this within this partially observable space, and how to reasoning meaningfully. So integrating these two kind of nodes, the instruct flow planner will construct a structured task prompt to be, this task prompt is sent to the code generator to generate a structured code. So once the code fails, the agent will receive an error message, and the instruct flow will trigger a workflow to automatically retrieve some failure information, retrieve which object caused the failure, and do the code level reasoning, and also diagnose what are the kind of symbolic constraints triggering this reasoning, and eventually this workflow will generate some symbolic constraints that is causing this failure. So this symbolic constraints is generated following some general form of symbolic constraint that we have formulated as instructed to the LLM agent. So this symbolic constraint contains a union of relational constraints and the physical constraints. So during the deployment of following this general form, the agent can automatically discover failures in the relational and physical form, and in a few short manner. And this is an example of how instruct flow can automatically do the code generation and the correction based on its symbolic constraint induction workflow. So the task is we want to put this green box into this green bowl, and initially the LLM generate version of Python code, but it failed because it didn't clear up the 2 boxes on top of this green box. So based on this error message, instruct_flow will trigger its symbolic constraint generation workflow and summarize these 2 symbolic constraints. One is the clear of the object 5, one is the clear of object 6. So based on this symbolic constraint, it will do the code correction and automatically inject this green colored piece of code to add in the planning steps to remove the the 2 blocking of blocks based on the guidance of this instruction. So the right side, the table shows that a series of different symbolic constraints that can be automatically discovered by the LLM by interacting with the physical task by itself. So this shows that agentic work, this kind of workflow and multi-LLM system has the capability to guide the LLM to automatically discover some meaningful knowledge in the physical world. And we tested instruct_flow on across of different manipulation problems, and it shows remarkable capability of improving the failure recovery rate for code generation, and it can achieve the state-of-the-art scores for this robotics manipulation. So to conclude, actually, we are actively working on this agentic AI research at CFAR to build up some AI agents that can truly autonomous and able to solve some long horizon problems and have the high self-improving capabilities. So with this regard, at current stage, we actively work on this agentic workflow optimization, which can help us decompose this long horizon problem into modular problems and let the LLM agent optimize how to solve the problem by itself. And also simultaneously, we care about how to ground this physical knowledge, ground the LLM's control with some physical and causal knowledge in the real world. So we developed something like instruct_flow, which can ground the robotics control with some symbolic knowledge to leverage the symbolic knowledge to help the agent to achieve a more robust physical control. And also we study on self-improving agency. So now we are stepping into the area of experience-driven self-improvement, where the agent can build up a memory, can use its own experience without training any world models to continuously learn from the physical world. And eventually we hope that with this kind of capability and roadmap, we can lead us to some truly emergent open world autonomy, where we can build up some agentic AI system to solve the new problems and unknown understand the unknown world by itself instead of and operate without human guidance. Yeah, that's the end of my talk. Thank you.
Thank you very much for your great talk. Yeah. So I want to know much more about your talk, but okay. So one thing is that you presented a kind of simulation robot. So
yeah.
Then your agent can add a kind of a constraint like this. So then, this agent has a visual information, or does it add this constraint only from the error message?
Okay, that's a great question. Actually, this agent is currently, this instruct_flow is operating purely with text-based observations and text-based error message. Mm-hmm. So there's no visuals, but it's possible to integrate some visuals and changing the LLM to some vision language models to do.
I see. But even though they don't have a visual information, but they know a kind of a world model inside, so then they can properly add this kind of constraint.
Yes, exactly. So it's the fundamental thing is that we want to generate some it's a code generation. So the code is still at the textual domain. So our current work, we didn't work much on integrating this text level code generation with visual features, but that's definitely meaningful. But currently we can express and discover those constraints from the text-based text-based representations, text-based workflow, constrained induction workflows, and the text-based error message. All these, in this modality. Yeah.
Good. Other questions? Yeah.
Thank you for the great talk. So currently, I think this pipeline is used for simulation, right? But probably after learning, probably you have a good agent. And then is it possible to apply to the real world agent directly after training in simulation? So
Thanks for the talk. Thanks for the question. Actually, that's a great question because, our current research paper, we didn't shift this system into a real robot grasper for testing. But actually, in the robotics domain, this kind of things we build can be directly shifted into a real robot for operations. So actually, though we didn't do it in our paper, but it's completely possible and very convenient to make it operate for the real robot. Actually, a lot of our baseline LLM-based agents, they integrate into the real robot, and everything is working like that. Yeah.
That's great. Thank you.
So other questions? Okay, so no? Okay, so then let's thank the speaker again. Thank you.
Thank you for the introduction. Hello, everyone. I'm Tiantian, a senior scientist at CIFAR A*STAR. Today, I'm going to briefly introduce some of my recent work on neighbor selection for graph representation learning. Okay, let's first get started with why neighbor selection is crucial for representation learning. Many real data that we can collect is in the form of graphs, which contain a set of nodes and edges representing the data samples and sample-sample relations. One of the key differences between graph data and other types of data is the edges among data samples. Holistically, we can also call it as graph structure, which describes some form of mutual relations between data samples. We can find a lot of such graphs around us, and many real analytical and predicting tasks directly come from these graphs. For example, users on the online social platforms such as Facebook and Weibo and their social ties can form social graphs where we can conduct user recommendations and clustering tasks. High-throughput medical images describing RNA profiling of cells can also form a graph where we can take RNA profiles of each cell and spatial distances as node and edges, respectively. Then we can predict pathological changes of these cells based on their graph representations. Atoms and chemical reactions, which are basic units of crystal and material, can also be formed as graphs, where we can use some AI models to learn their representations for downstream tasks such as material design and property predictions. To conduct predictive and analytical tasks on graph data, many approaches have been proposed since the year of 2000. To date, graph neural networks have shown to be one of the most powerful tools for graph learning tasks. Although many graph neural networks are developed, they share a similar paradigm to learn representations for various downstream tasks. For each central node, messages from all its neighbors are firstly generated. Typically, the message from a neighbor is the neighbor representation multiplied by some weight, such as attention coefficient representing the neighbor importance. Then the output representation of the central node can be generated by some computations regarding messages and the representations of the central node, such as average, with its sum, max, or min functions. Besides the representations of each node, we can see that how we determine the importance of neighbors, and based on that, we select the neighbors to generate the representations is crucial, as it may reveal neighboring interdependency in the graph and potentially determine the representations learned by the graph neural network. Besides graph neural networks, other popular deep learning models, such as transformers, their forward learning process can also be seen as the generation of graph representations. We all know that the representation of each data token in the transformer model is generated by the product of self, attention vector, and the corresponding representations of other data tokens. If we treat each data token in this process as a node, and each attention coefficient as an H weight, a complete graph can be constructed to represent the holistic relations between the central data token and its neighbors. Thus, research on neighbor selection is not only important for graph neural networks and graph learning tasks, but it also has the potential to revolutionize the design of other AI models, providing robust and accurate AI system for various real problems. Together with my supervisor, Professor Oh Young-Sun, our team has been working on neighbor selection for graph representation learning for several years. Generally speaking, our methodology is designed according to real-world observations so as to address the practical challenges in existing graph neural network models and other related AI systems. We find that most graph learning systems do not fully utilize the joint effect of data features and structural properties. Thus, their learning capabilities are limited. We then design new neighbor selection strategies to allow graph neural networks to generate representations carrying desirable structural properties, such as node clusters and multimodal structural relations, so as to improve the overall performance of AI models. Many of our works have been published in some top-tier AI conferences and journals and supported by national research projects. In what follows, I will briefly introduce some of our representative approaches and applications we use our approach to solve. Okay, let's move to general methods developed by us for neighbor selection. The first approach is about modeling the polarized message passing phenomena in graph neural networks. We observe that many real-world data are created differently, thus demonstrating polarized properties regarding node features and the graph structure. One of the most representative properties are homophily and heterophily. Based on this, we propose a simple but effective approach which leverages both similarity and dissimilarity measures to formulate the functions for computing weights between neighbors. Then we use it to select truly correlated but sparse neighbors to involve into the generation of output representations. Compared with conventional approaches, our method further dig into the graph structure to find a sparse but informative subset of it for generating graph representations. Our theoretical analysis also shows that a graph neural network equipped with our approach is more possible to generate a correct label for the node in the graph. Our approach is quite flexible and can be integrated with many existing graph neural networks. In our experiments, we leverage the polarized message passing functions to design new graph convolution, attention, and page rank networks and compare the performance with those representative graph neural networks. In some challenging tasks like node clustering, the performance gain of our approach is up to 80%. of performance improvement, showing that our approach is very effective in graph representation learning. Besides, we also investigate the node distances in the original graph dataset and find that many neighbors are very distant to the central nodes. While our approach allows graph neural networks to learn such sparse graph structure and leverage it to generate accurate representations. The second approach is about modeling the clustering properties for graph representation learning. In our preliminary experiments, we find that the attention coefficients learned by existing graph attention networks are linked to average the age weights, which cannot discriminate nodes well. On the other hand, modularity is a well-known measure evaluating the community affiliation of each node in the graph and can be maximized to find the optimal community structure. Thus, we derive a differentiable form of modularity optimization and then use the model parameters involved into the computation of graph attention to parameterize this objective. As a result, the modularity can be optimized along with the training of a graph attention network. Node representations are mainly generated by neighbors within the clusters, and the learning capacities of graph attention networks can be improved. We compare our approach with prevalent graph neural networks. The results show that our approach can improve the clustering and classification performances by up to 10%. We also analyze the community structure of the test graph datasets and compare it with the attention coefficients learned by the proposed graph neural network. We find that the attention coefficients within clusters are indeed much higher than those between clusters. This means our approach can effectively capture the cluster structure when selecting neighbors for generating data representations. And considering cluster structure is a good way for learning meaningful data representations. The third approach considers cross-model relations for neighbor selection. In some real-world tasks, such as road network representation learning, the node relations can be characterized by multiple sources, such as graph and street view images. This data may provide complementary or even contradicting features of node relations. From geography, we know there are two famous laws. The first law describes that similar road segments should be spatially nearby, while the third law of geography claims that if the configurations, for example, styles, are similar, those distant road segments might still be similar regarding functions. Previous works shows these two laws are important for road network representation learning, but no one has successfully merged them together in the AI model. To address this, we formulate two different augmented graphs based on the first law and the third law of geography. Then we build the 76 graph convolution network to fuse the neighbor relations to learn representations, and use two different contrastive laws to enhance the impact of first and the third law of geography in the learning process. The node representations in our model are generated by considering both geography laws, showing that our design can effectively fuse diverse graph signals to select neighbors for learning representations. We also compare our graph neural network with a number of state-of-the-art approaches to road network representation learning. In in different downstream tasks, our approach performs robustly compared to other baselines. Notably, the performance gain of our approach is up to 171%, showing that our fusing strategy for selecting neighbors is very effective in many challenging learning tasks. Together with the performances of the other two introduced approaches, we can see that appropriate design of the neighbor selection is crucial for accurate and robust representation learning. Besides designing new approaches to neighbor selections for graph representation learning, we also apply and adapt these approaches to solve some real world applications. In general, we have applied our methodology to solve some scientific problems, such as bioinformatics, biomedicine, and material sciences. The data from these real-world problems can naturally be modeled as graphs and the graph structure. To some extent, this is very important for the quality of the learned representations. Compared with conventional AI models, graph-based approaches can fully take into the consideration of the structural properties among data samples, learn data representations from sparse but robust structures, thus improving the predictive and analytical performances. Given the different downstream tasks, we can design graph neural networks having different neighbor selection strategies, then learn meaningful representations for these tasks. Let's see the first application. It's about AI for DNA storage. DNA storage is a popular application of AI, which mainly uses AI models to encode data into DNA sequences. Then, laboratory can make these DNA sequences for data storage. Compared with a traditional storage approach, DNA storage is very stable, lasting many years. However, AI-based DNA storage methods suffer from information and structure loss, causing many errors during the encoding process. To address these challenges, we designed a novel graph neural network encoder. We use Kolmogorov-Arnold feature transformation to capture the correlations between DNA segments and data to store. Then we use the transformed data features to compute the attention coefficients for generating graph representations for DNA encoding. To allow the proposed approach capture the stable biological structure of DNA sequences, we additionally propose a single-stranded loss to regularize the learning process. Through the test of comprehensive experiments, our approach shows lossless and efficient data encoding process compared with traditional pure coding approaches and recent AI-based methods. In an ongoing research project regarding AI for drug discovery, our team faced the following challenges. RNA target discovery requires measurements of molecular information within disease tissue, for example, spatial omics. However, spatial omics data is difficult and expensive to collect. As spatial omics data and high-throughput digital pathological data describes the molecular profiles of cells, we are able to formulate them as graph and design novel graph-based classifier and generator to predict cell types, analyze the properties of RNA targets, and generate de novo spatial omics to pair with other pathological data to address the data imbalance issue. During the past 1.5 years, our team have collected a huge volume of pathological data. We are now targeting training a foundation model for digital pathology for the ASEAN cohort. I think this should be the first biomedicine foundation model for ASEAN people. Yeah. In another recently awarded AI for Science project that is collaborated with my supervisor, Professor Oh Yung-sun, Dr. Haiyan, and scientists, other A-star scientists and researchers from Imperial College of London, we are planning to build novel AI approaches to design novel catalysts and predict their key properties. The situations we are facing is also very challenging. We are given a huge volume of ideal catalysts generated by multi-scale simulations whose quality of fidelity is always low, and a small volume high fidelity real catalysts and materials that have been tested by the experiments. Designing a new catalyst regards to search and predict the optimal material structures given the design space guided by this given data. Our material scientists tell us that the complexity of this design space is up to 10 to the power of 12. This is intractable for empirical experiments and multi-scale simulations. As previously mentioned, this material and catalyst data can also be modeled as graphs. And our original thinking of a catalyst design problem should be based on sufficient knowledge of catalyst structure and the properties. Therefore, we propose a multi-fidelity graph-based encoder to play as an important role in the foundation model for catalysis and the surface sciences. For this encoder, we leverage our expertise of neighbor selection to design new learning paradigms that allows the model to learn catalyst representations in an efficient and robust manner, significantly improving the training speed and accuracy. After aligning with the latent space generated by the text encoder, we are able to leverage conditions on multiple key features of catalyst structures and semantics to guide the generator of the foundation model to design preferred new catalysts. To further enhance the generative performance and automate the optimization, catalyst design, and discovery, we also propose a new agentic AI framework, which is done by my colleague, Dr. Haiyan. Here I skip the technical details of the agentic AI part. Together with the agentic AI framework and the downstream experimental validation conducted by our material scientists, the proposed foundation model is expected to design new catalysts satisfying multiple metrics from learning and the scientific domain, thus accelerating the discovery of new catalysts. This is the list of the references supporting this presentation. And at last, I would like to express my sincere gratitude to my supervisor, Professor Oh Yung-sun, my department director, Professor Eva Cang, and all my colleagues and group members. None of these mentioned works can be achieved without any of you. I would also like to say big thanks to Professor Sugiyama, Professor Suzuki, and Dr. Nitanda for organizing this workshop and letting me have this opportunity to share my work. Thanks very much. That's all for my presentation. Yeah, thanks very much for listening.
So I have a question. So can you hear me?
Yeah, can. Yes, please.
Okay, so in the last part, so you are planning to apply your method to like a catalyst generation.
Yeah.
So then my so my impression is that in a graph, so then the nodes should be fixed. So then, so I'm wondering how to generate a new catalyst. So then, do you produce a new node, or so? Okay, maybe the catalyst is just one graph, or just
maybe I can explain this with a simple example. For new catalysts, we also know that those catalysts should be composed by some known atoms and chemical reactions, right? So that means if after the foundation model capture enough or sufficient knowledge of the representations of those material structures, we can use this foundation model to generate new compositions of atoms and the chemical reactions formulated as graphs. That's a basic generating process of the novel materials. For catalysts, because it is also very similar to general material design, we can also follow this process to design new catalysts. Yeah.
I see. Yeah, thank you. So then, is there some possibility to, well, combine with like a diffusion model, like so? For example, some.
Yeah, definitely. I think you can see this slide, right? In the foundation model, we have different modules. One is encoder, that is graph-based. Another one is a text encoder, that is used to generate the semantic conditions for catalyst generation. We want to align the latent space generated by the encoder and the text graph encoder and the text encoder. After that, we use the aligned latent space as the conditions to guide the generator that will be possibly diffusion based to generate new catalysts. Yeah.
I see. That makes sense. Yeah. Thank you.
Thank you for this talk. I have a question that if you can generate a new catalyst, how you validate that this new catalyst is okay? I mean, is
if we want to validate the quality of the newly generated catalyst, it can be conducted in maybe two ways. The first is we just based on the results predicted by the foundation model. Because when we train the foundation model, we may have different properties formulated as different objectives that will be used to train the model. When we generate a new catalyst, it will also generate or predict some key properties of these newly generated structures. Based on the values of these newly predicted properties, we may preliminarily validate the quality of the catalyst. If we want to optimize the design of the new catalyst, we may leverage some automation methods, for example, the agentic AI part to further optimize the generative process. After we obtain the optimal catalyst structures, we will send these candidate structures to our material scientists. They will do some further tests, for example, synthesizability and lab-based experiments to validate all the possible properties and features regarding the key features for the catalyst performance. I think if we want to fully validate the catalyst structure, we have to do both of these two steps. Yeah.
Okay.
We cannot generate perfect catalysts without the guidance expertise from chemical and material science. Yeah.
I think that evaluate the catalyst generation may be a long period cycle, right? So because
Yeah.
we need the material science to maybe synthesize this catalyst with the maybe the structure you generated, and then
Yeah.
Okay, thank you.
Yeah, true.
Thank you. So other questions? Okay. No? Okay, so then, yeah, so it's good time to finish this talk. So let's thank the speaker again. Thank you.
Yeah. Thank you. Bye.